sklearnensembleBaggingRegressor. Description: Bagging regressor is an ensemble method that uses bootstrap aggregating bagging to create multiple decision trees and then averages their predictions. This helps to reduce variance and improve the accuracy of the model. It is particularly useful for dealing with complex datasets with high variance, where a single decision tree might overfit the data. Inputs: Base estimator. This is the base estimator used to create the individual decision trees. It can be any estimator that implements the fit and predict methods, such as decision tree regressor. Nestimators. This parameter controls the number of decision trees to create. A higher number of estimators generally leads to better performance but also increases computational cost. Max samples. This parameter controls the maximum number of samples to use when creating each decision tree. A value of 1.0 means that all samples are used, while a value less than 1.0 means that a random subset of samples is used. Max features. This parameter controls the maximum number of features to use when creating each decision tree. A value of 1.0 means that all features are used, while a value less than 1.0 means that a random subset of features is used. Bootstrap. This parameter controls whether to use bootstrap sampling when creating each decision tree. If set to true, each decision tree is trained on a random subset of the samples with replacement. Bootstrap features. This parameter controls whether to use bootstrap sampling for features when creating each decision tree. If set to true, each decision tree is trained on a random subset of the features with replacement. Outputs: Predictions. The model outputs predictions for the target variable. These predictions are based on the average predictions of the individual decision trees. Steps: Bootstrap sampling for each decision tree. A random subset of the training data is selected with replacement. Model training. Each decision tree is trained on its respective subset of data. Prediction aggregation. The predictions from all the individual decision trees are averaged to get the final prediction. Metrics: Mean squared error (MSE). This metric measures the average squared difference between the predicted and actual values. R-squared. This metric measures the proportion of the variance in the target variable that is explained by the model. Visualization plots. Feature importance plot. This plot shows the importance of each feature in the model. Residual plot. This plot shows the difference between the predicted and actual values. Fine-tune parameters. Nestimators. Increasing this value generally improves performance but also increases computational cost. Max samples. Decreasing this value can help to reduce overfitting but may also decrease performance. Max features. Decreasing this value can help to reduce overfitting but may also decrease performance. Uncertainty methods. Standard deviation of predictions. This method provides a measure of the uncertainty in predictions by calculating the standard deviation of the predictions from the individual decision trees. Challenges and fixes. Challenge 1: High variance in the predictions. Sample use case that resulted in challenge 1: When the model is trained on a small dataset or a dataset with a lot of noise, the predictions can have high variance. Fixes to challenge 1: Increase the number of estimators nestimators to reduce variance. Decrease the value of max samples or max features to reduce the variance of each individual tree. Challenge 2: Overfitting the data. Sample use case that resulted in challenge 2: When the model is trained on a large dataset with a lot of features, it can overfit the data and perform poorly on unseen data. Fixes to challenge 2: Use a smaller number of estimators nestimators to prevent overfitting. Increase the value of max samples or max features to reduce the variance of each individual tree. Use regularization techniques, such as L1 or L2 regularization, to prevent overfitting.